for that introduction. Yeah, so I'm Melvin. I'm a research engineer at Studio Raccoons, kind of like a newly announced thing. I don't think any of my colleagues are here, so it's okay. I'll just say whatever I want. But just a little bit about what we do at the studio. So this is one of the products that we've built and I've been working on recently. It's a swap aggregation, so it's running on Solana blockchain. And what we're computing here is this. I can't really see. It's a bit dark, but it's a route through various different decentralized exchanges to obtain the best possible amount of output tokens. But in any case, it turns out that the talk I'm giving today is actually somewhat similar, but it was done several years back at a different company called the Intelligent Warehouse. And let's see if this works. So because this is on a Google Meet, it might not look right. Hang on. So just to give you a sense of what happens in a warehouse, there's this pretty nice video that, oops, how does that not work? Okay, sorry, give me 1 second. Do you see? I think there will be no audio.
Yeah, there will be.
There will be?
Yeah, there should be.
There is no audio. So,
No?
anyway, they're talking about, this is, I think, in Singapore, preparing for Amazon Prime Day a couple of years back. This is from Tech in Asia. So this is what happens kind of when you do like a order with Amazon. So they have this shelves upon shelves of products. And one thing I think he said, you can't hear it, is that the products are actually randomly placed into the shelf. So it's not like all of one product is in one shelf. They are randomly distributed. And then there's this person, I don't know whether we saw that already, would push this cart and go to different shelves and get the products in your order. And presumably they do multiple orders at the same time, right? Because some orders might be very, very small number of items. And then they'll just place a sticker and then they will ship it to your place. Okay, unfortunately you can't hear the sound. So let me get back to, oh, sorry. Go back to this. Whoa, what happened? You went to the last slide. Sorry. Okay, so that was the video. And so let me just take a step, well, like 50 years back. So that problem, you think about the picker, right? Pushing this cart. It's actually quite similar to what you do as well when you go to the supermarket, right? Like there'll be this like aisles, and then you would go and then you would find the aisle with the product you want to buy, and then you put it into your cart, and then you go to the next product and so forth, right? One thing to say about this is that a large majority of the time of these pickers, the name of the role of the person is called picker, and the vast majority of the time actually is not picking the product, it's actually walking. Right, because the warehouse is vast. I mean, they have a lot of different products. A warehouse typically is much larger than your typical retail shop, right? Because warehouse is located in this far off area where they have like more land to build this bigger storage facilities. And so the task really is, how can we help like these pickers, right? I mean, reduce the time spent walking. And obviously this will increase the throughput of the e-commerce service, right? Because we can package the orders quickly, you can send them out, and you can do more of them within the same amount of time, especially on like peak periods like Prime Day or big sales and things like that. So this problem is obviously not a new one, but it's in a new context because it's in a warehouse. So what would be like the typical name for this? So it's actually called the Travelling Salesman Problem, because I think in the past I think of door-to-door salesmen. I don't know how true of this, like they actually developed this problem because of that, but it's a nice story, right? So you have this salesman who is going to go around, I think these are the 48 states of the United States. So if you imagine this salesman going to every state to, oh, darn, what happened? I thought Meet was supposed to work. Can I get some help?
Yeah.
Wait, is that me? Oh, that's my screen. That's my screen not working. Oh, meeting's ended. So maybe, I think on the non-paid account, there is a time limit on how long the meeting can run. And we have probably overrun the duration of the Meet account. So we've got to start the Meet again so that you can see. Never mind, I'll just continue first while the organizers get the thing going. But you can't see what I'm saying. But anyway, I was just telling you about this. I think you can imagine I was showing the map, right? So there's this salesman who's going to go to all the 48 states to do some sales presentation. So the problem will be like, how do you like order the states, right? Which state do you go to first and so forth? Oh, are we back in the meeting? Okay, so let me just reconnect. Oh, I gotta key in the thing again. Darn. Okay, yeah. Okay, I guess we'll do for the next like 1 hour or so, right? The Meet stream is. Is it okay? Okay, I think we're back. Great. Come back to this. It's a good thing I have a 45 minute slot. Okay. I was a little bit worried. Actually, it's quite long, 45 minutes. Okay, anyway. So this is 48 states, which was solved in 1954. And actually, this was a very big moment because, so some of you might recognize, so it was solved by 3 people, Danzig, Fulkerson, and Johnson. Danzig is known as the father of linear programming. So in fact, it would not be surprising to tell you that this was solved with linear programming. But then you realize that actually TSP is not a linear programming problem, or not traditionally solved with linear programming, right? And hence, that's why this was a big breakthrough, because they managed to use this technique, linear programming, to solve this problem. And it was a fairly large instance at that time. So, skip forward more modern times. This is another TSP problem. So the TSP problem is to find the shortest tour, so-called, the shortest tour to visit all of the points. So in here will be to visit all of the 48 states. In the picker's case is to visit all of the shelf locations with the items in the order, right? So you can see that they are essentially the same problem. Okay, so this is a much bigger instance. So this is still the United States, but now instead of the 48 states, they're looking at 49,000 historical sites. But let's say you're going on this grand tour of the United States. You're going to visit all the historical sites. There are approximately 49,603 of them, and you're going to walk between all of them. You're going to do a lot. You're going to walk. So we're trying to find out what is the minimum walking distance to visit all of these 49,000 sites. And this was solved by William Cook et al. In 2016 using substantial CPU power. I think largely still using the same technique as Danzig, Fulkerson, and Johnson, but obviously with much more, some algorithmic improvements as well as CPU improvements. So about 178 CPU years on this 350 million meters. But this is a gigantic instance. So although TSP is a very difficult problem, actually we can really solve very, very large instances if you devote enough CPU time. Okay. And this is actually Cook. This is William Cook. This is from his talk. It's on YouTube. So if you're interested in the history of the TSP and so forth, I really recommend watching William Cook's talk called Information Computation Optimization. I like this specific slide on his talk actually because it shows something really interesting. In fact, he shows the linear programming formulation if you're into that, but it's not important. But more importantly, he shows how can you prove that you found the minimum tour connecting all the points, right? Because you can always find some tour, but how do you show this is minimum, right? And for those of you familiar with linear programming, you might recall something called the primal dual. So the primal is the, let's say, the minimum tour, and the dual is a kind of maximization problem. We find the maximum something, right? And in the classic primal dual theorem, it says that, well, at the optimal solution, the solution of the primal and the solution of the dual will be equal, right? Because the primal is trying to minimize, right? And the dual is trying to maximize, right? So one comes from up to down, minimization, and one is a maximization problem. And a very special point called the optimum solution, the two will meet, right? So when that happens, you know that your answer is optimal because you found both primal and dual, and they're equal, right? So why this slide is interesting is because it shows you both the primal and the dual, right? So let me try to explain. The primal here is straightforward. The primal here are the lines, right? The black lines connecting the points you want to visit. Because the primal is the TSP, right? We're trying to connect all of these black dots. There's some black dots. We're connecting them with black lines. So that there is a tour that goes through all the black dots and comes back to itself, but the shortest possible. Right? Now, what is the dual? The dual is this funny moat. I'll call it a moat. Right? Can you see this like bubbles? So we're drawing this like radius or this moat around some of the dots. Right? So one thing very special about this moat or this bubble is that any tour must must cross the moat twice, right? Because you must go in to hit the points inside and then come out to go elsewhere, right? So there's this going in, coming out, right? And so you can sort of see that if you try to expand the moat as far as possible, this is the maximization problem, how to draw these colored bubbles, right? And if you look at the radius of these bubbles, if you take the double of the radius, right, that will have to be equal to the tour, because the tour exactly goes in, crosses the moat, and then crosses it again on the way out. So the two answers will meet. So these bubbles or the moat is actually the dual of the TSP, and it gives you a certificate that your answer is optimal, because the width or the radius of the moat, the sum of all these radius or radii equals the twice of the radii equals the length of the tour. Anyway, let me move on, in case you're not a fan of linear programming, which this is as much linear programming as I will say in this talk. Okay. And again, if the talk was not enough, I watched the talk and it was not enough, there is the book, also by William Cook, which you can find in our National Library. It's called In Pursuit of the Travelling Salesman, wonderfully written. Again, you can see here he shows the 48 cities by Danzig, Parkinson, and Johnson, because that was a really landmark result. That's the briefcase, by the way. Okay. And of course, we have also this seminal result by Richard Karp, 1972, TSP is NP hard, meaning in practice, we don't expect there to be efficient solutions. And there is kind of a follow-up to that result by XKCD, which talks about some of the complexity involved, right? You could sort of brute force all possible orderings of the cities or the order. That's something like n factorial. And there's this other, in fact, there's this, interestingly, there's this n squared to the n algorithm. That is, I think Richard Karp was one of the inventors of the one in the middle. Richard Karp from the slide before. And then there's the other alternative, right? Which doesn't involve going around and trying to sell something. Any case, so let me come to the work I'm trying to focus on, which is in the warehouse, TSP in the warehouse, right? So that was just general TSP results and so forth. So typically we will model a warehouse like this. So there's these long vertical spaces where you can walk. That's called the aisles. And then there are these, there are many of them. And then there are these horizontal spaces which cuts through the aisles. So here you can see three of them. One at the very top, one in the middle, and one at the bottom. Right? And unsurprisingly, these are called the cross aisles, because they cross they allow you to cross between the aisles. The aisles are the columns, right? So you can imagine we will build like a graph model. So to help us represent it, we'll build like a graph model so that there are nodes at the intersection points as well as there are nodes at where the products are located, right? So 1, 2, 3 are where we have to pick up 3 different products, and D is like the starting point of the picker as well as the ending point. So imagine you're going to start from D and then somehow pick up the things at locations 1, 2, and 3, and then go back to D, right? So that will be the tour we're trying to build. And as it involves walking, we want this distance to be as short as possible. Okay? Right. Alright, so let's come to the first article I will talk about. So this is work done by 2 French researchers. I'm going to not pronounce the name very well, but it's Adrien Cambazar and Nicolas Catus. And this is a paper published in the European Journal of Operations Research in 2018. So we'll take that same thing, but we will abstract it out a little bit. So again, we have these black dots, right? Again, the story is always we have black dots, and we want to draw some lines to connect the black dots. Okay? But because this is the warehouse, so the warehouse structure, if you notice, we can only walk in one of 2 ways. We can walk along the aisle, which means go up or down, or we can walk across the aisles, which means go left or right. Right? So it's a little bit different from what Cook was talking about, right? Where you can see these funny slanted lines. So there are no slanted lines here. All the lines are either vertical or horizontal, right? And in fancy language, we call that rectilinear. That's fancy language for saying the lines are either horizontal or vertical. It's not a complicated concept. It just means when we connect the black dots with lines, the lines must be either horizontal or vertical. That's all rectilinear means, right? Okay, so this is again the black dots. To make it easier for us, because we know the lines are going to be either horizontal or vertical, we'll draw some extra lines, like to make a grid, right? So for every black dot, we draw like its vertical line and the horizontal line for every of the black dots, right? Because these are the gray lines are where we can sort of reach the black dots, because we can only move horizontally or vertically, right? In this rectilinear restriction, which turns out to be extremely important. This actually allows us to solve this problem much more efficiently than if you allow slanted lines. Right? We'll try to, hopefully I'll try to explain to you the intuition why this rectilinear restriction helps. Okay. And then again we build a graph, right, as we do previously. But we build a graph along these extra lines, right? This other thing, the technical word is just called a Hanan grid, but not a very difficult concept. We're just adding this vertical horizontal lines for every dot. And then we just add edges. And then we have every intersection is a vertex. So we have extra vertices, not just the black dots, we have some extra vertices, which are like the intersection points, right? And then we add edges because this is a graph, right? So it's no longer a grid. A grid is just a bunch of lines, right? What is a graph? A graph would be vertices and edges, right? So the vertices are the points we want to reach, as well as all the intersections, the gray ones. And we add edges. We need 2 edges for every sort of line, because you might want to go in both directions, right? Like you want to go up somewhere and then later on come back down. So to represent that, we add 2 edges. Okay, so this is the graph G. Okay, so what is the answer we're trying to find? Right, which is this tour that connects all of the black dots, but can only move horizontally or vertically, and has to be as short as possible. Right? It turns out that it has to be a subset of the edges. Right? So this is one possible tour. Right? So this is the whole graph, right? And this is the tour that would do the job. Right? You would reach all of the black dots. And I don't know if it's the shortest possible, but this is certainly one valid. It's probably not the shortest possible, right? Is there a way to say that this is not the shortest possible? I mean, let's do some audience participation. Like, can this be the shortest possible tour, or not? No, no. Why? Yeah, exactly. That's a great answer, right? Because here you see we have this like bend here, right? But why would someone walk here and then take this like roundabout way, right? You would just go straight, right? I mean that still satisfies what we want to do. We're going to go to all the black dots, right? And it's obviously like shorter, right? I mean, at least obviously from this picture. Oh, yeah, it's clearly shorter because this is equal to this, right? But we got rid of these two horizontal pieces. We don't need them anymore, right? So that's a better tour. But anyway, this is just to show you one example of a tour. This is not the optimal tour because of that reason, right? So good, you've been paying attention. Okay, okay. Let's move on. Oh, right. And then after we have this, let's say we have this bunch of edges. These are the edges we're going to use, right? Then you might wonder, but how do we actually do the walking, right? Because the edges don't really say how to walk. It's just edges. These edges are not directed, right? That problem turns out to be quite simple. We just sort of figure out the directions. Okay, so we just figure out the directions after the fact. So we decompose the problem into a few steps. First, we decide what edges we're going to use, which is this problem, and then we figure out how is this person going to walk by adding their directions, right? So that part, I'll leave it to you to think about how that could be done. So if you're given only the edges, how would you figure out the direction? It's not too difficult, so I will skip it during this talk. So I'll assume we have a procedure for doing that, okay? And we can do this very efficiently, figuring out the direction of the edges. Okay, now this is the diagram that I spent days and I still couldn't understand. So I'm hopefully going to try and explain to you this diagram, which is essentially the gist of Canvasar and Kertugh's algorithm for solving this problem, by finding the minimum tour. Okay, so here we have this, again, the story with the dots. So we have the black dots, which are the place we want to go, and we have this, we don't draw the whole graph. Here you can see the Hanan grid, right? The Hanan grid is the gray lines. But you also see some solid lines, right? Can you see that in the gray area, the shaded portion, there are some solid black lines, okay? So you can think of this as like a partial tour. So we have connected some of the stuff, but it's not complete because we didn't go everywhere yet, right? So the gray area have some solid black lines, and it shows that we have connected up some of the stuff in the gray area. Okay, it means we found some way to connect them together. Then there are the, let me say, I think here it says dashed lines. There are the dashed lines on the white side of the diagram, right? So this is one possible way to complete the whole thing, right? So if you take the dashed lines plus the solid lines, it actually is a complete tour, okay? But why this diagram is important? Because they're trying to tell you, okay, let's say we have a completed thing. Can we, again, do this decomposition? Can we chop it into two parts? The parts in the gray and the parts in the white, okay? And if we can somehow like maybe solve the gray area, we can combine the results together. So again, it's this flavor of dividing something, this big problem, into a smaller problem by doing this boundary, right? And then there's this dark gray region. That's kind of like the boundary, right? Can you sort of see like a dark gray region? It's the boundary between the light gray and the white region. Okay, so the dark gray region actually is the most important bit. The key here is really that we don't really have to care about what happens in the gray region, the entire light gray region. We just have to record some information about the dark gray, the boundary. Right? So this lets us define the sub-problems. Okay, maybe you'll get clearer later, hopefully. There's some other diagrams that makes it more clear. So what is the key information about this region is, for each of the vertex on the boundary is this dark gray thing. We need to know two pieces of information, right? One is what is the degree of that vertex? Is it unconnected? If it's no degree, we'll write 0. Okay, so that's why the first two are like 0, 0. because there are no edges, there are no dark edges, right? They're not connected to anything. So for the degree, we'll just write 0, okay? And then for the next one, the third vertex, right? The vertex at row 5, here the symbol used is U, right? U means the degree is odd. Okay, so that's all it means. U just means the degree of that particular black vertex at row 5 is odd. The degree is 1, in fact. Okay, but it turns out even the degree is 1 is not important. You just have to know that it's odd. Okay, so the degree is odd. And the same for the rest. I think the degree is the easy part. Oh, and then when you say the letter E means the degree is even. So we only have to care about whether is it odd or even, or is it 0. 0 technically is even, but for the purpose of this method, we need to distinguish between 0 and even. Okay? So we have 3 possible values there. 0, U, which means odd, or E, which means even. Right? Okay. The second number actually is also not too complicated. It just means which component is it? Component in the sense that which piece does it belong to with the black lines, right? So for the ones that are 0, they are not connected to anything, so we just put a dash. There's no component, right? They're just freestanding, so you just put a dash, right? For, let's say, the one on row 5, right? The one which says U, 1. The first component from the top, we'll just call it component number 1. Because you can see this structure at the top, right? This is one connected piece, right? Because of the black lines, right? So we'll call this component 1. Just that's by definition. The first one from the top is component 1, okay? So we'll call this, we'll just write 1 here. This belongs to component number 1. This vertex. So actually this is the same because this is connected. Right? So this is also component number 1. Okay? And then there's this bottom chunk here, which is all connected. And because it's the second one from the top, we'll call this component number 2. Right? So we'll just write the ID of the component. So we'll just say even, and it's in component number 2. And same for the rest. Okay? So that's the critical information. And this is in fact the way we define the sub-problem. How we decompose the problem into different smaller problems, right? To solve, right? By remembering this sequence. So this problem is defined by the stuff in the brackets. This particular sub-problem. Okay, so let me go through a real full example. Hopefully you will understand how it works now. Alright. So the way this works is we will run through the edges of the graph in a particular sequence. So we'll consider this vertical edge. So I'll call this edge number 1 because we'll consider this edge first. And then we'll do this edge here, edge number 2, and then we'll do this horizontal edge. Okay? And then actually the algorithm goes on and on. I mean, it just keeps going and going and going. But lack of space, so it doesn't show all the steps. Alright? So we're starting with this simple graph with 4 black points, and we're going to connect them with vertical or horizontal lines. Okay? And again, we will start by considering each edge. Right? And then first one, second one, then third one. Okay? Okay, so let's see. So at the very beginning, what is the sub problem that we have? The sub problem that we have is basically no edges, nothing, empty. Right? Nothing means everything is disconnected. So it's 0, 0, 0. Right? Because there's nothing, no edge at the very beginning, right? And dash, dash, dash because there's no component. There's nothing, right? Okay? So in the very first step, we're going to consider this edge now. Now, back to what I said about the graph, right? What are the possible cases for this edge? How might we use this edge? How many cases would there be? There will be 3, it's kind of obvious here. So what are the 3 cases, right? It's because for this edge, either we never use it, we never touch it. So let me go back to this. It's like this, right? So what are the cases for edge? It's like this, we never use it. Or like here. We don't use it. That's one situation, right? Another situation is when we use it once. Like this. We use it once. Okay? And the final situation is where we use it, there's no vertical example, but we use it twice. Because you go in and come out. Okay? So there are only 3 cases. Which is quite natural, right? Because either we never use it, or we use it once, or we use it twice. Okay? So, yeah, okay. The meat is a bit slow. That's why there are 3 arrows. Okay, the 3 arrows actually represent the 3 cases for that edge. Okay. So again, if you never use it, what is the resultant new problem? Right? Of course, it's the same lah, because we never use any edge, so the problem is still the same: 0, 0, 0, dash, dash, dash. Because we didn't use this edge one. Okay. The middle case is actually using it. It's a bit small here, but it means using it twice. Suppose we use this edge twice, right? We actually don't know what is the real answer, so we kind of like try everything. But it turns out to be fairly efficient still. So we use it twice, right? What is the result, right? You can see that it will be 0 EE. Why is it E? Because we use it twice. So now these 2 nodes here and here are going to be even, because there are 2 edges now, right? And then it's going to be dash 1, 1. Because now there's one component. There's one component containing this 2. And this case is when we use it once and so forth. Okay, but so that's all you know to understand this diagram, right? And then you can do all the rest. So the rest is again the same, but in this part of the graph, we've dealt with H1. Now we think about, what about H number 2, which is this one, right? Again, we have 3 cases. Either we use it 0 times, 1 time, or 2 times, right? And that leads to the next, this L equals to 2 layer, right? And so on and so forth. It just keeps going on and on, right? So as a concrete example, if you do this, if you go along this path, right? You use the first edge twice, the second edge once, and the third edge twice, right? So it's like a twice, once, twice. You end up with this thing. So this is twice, this is once, this is twice. Does that make sense? So if you go along this solid lines, it's showing you first edge twice, second edge once, third edge twice. It looks like this, and this is the resultant ID of this problem, right? Because it's odd. This is odd, right? This is 1, is odd. This is 3, it's also odd. So it's UU. This vertex has 4 edges, so it's even. And they're all connected. Oh no, this vertex, sorry. It's talking about this vertex, and this vertex. So they're all connected, right? So it's 1, 1, 1. Okay? Alright, so this is the most complicated part of this talk. So get this over. Anyway. Oh, good. And then the code looks like this, but the code doesn't matter. The code just does what I just said, but it looks quite hairy, but it's actually not that bad. So one thing that surprised me when I did this implementation, again, unfortunately for the lighting, you can't really see. This is my implementation of this in Python. So any of you are Pythonistas. It's actually just this. It's not that complicated, right? If you kind of understood what I said about for every edge, we're just trying all the 3 cases, right? And then we record down the new problem and we restore the answer, right? So it just looks like this. Anyway, not really important, but it's just to see that actually it can look quite similar to. But in fact, I would argue it looks maybe even simpler than the mathematical notation over here. But anyway, not important. This is roughly how fast it runs. So if you have 200, n is the number of aisles. N is the aisles, the vertical aisles. H is the horizontal cross aisles. So it is not super fast, but it is reasonable. Okay, so let me try to finish off. Anyway, I think my time is almost up, like 10 minutes, which is just enough time. So that was the paper in October, which talked about the rectilinear TSP, right, which was connecting the black dots with vertical horizontal lines. But if you think about it carefully, it doesn't quite solve the picker's problem, right? So this article, the introduction of a new author, Lucy Hansar, would approach that, try to solve it with the picker. Right? What's the difference? Well, in the case of the picker, it's not just, these are the edges now, right? The picker actually has, the dots are actually along the edge. Because the points you want to pick are along the aisle, right? And just now we said, well, you know, the H only has 3 cases. Either you go, you use it once, you use it twice, or you never use it, right? But in the real situation, you have the products that you want to pick up along the edge. So there are a little bit more than 3 cases, right? So let's see. Turns out that there are something like 6 cases. Actually, yeah, actually we don't care about direction. So these two are kind of the same. This is just going up and going down. So if you notice, we don't care about direction. So this two is using it once. So we don't care about this. Now, these two are actually different now. Can you see? C and D are different. So C and D is basically saying, I will pick all of the items coming down from the top and going back to the top. This is a new case, right? So this is not reaching here at all. We never reach this point. So we just come in on top of the aisle, pick everything, and then back out from the top. This is the new situation, right? And then there is the inverse of that, where we come in from the bottom and we pick everything and then go back from the bottom, right? And then there's this case, which is the same as just now. We go both directions. So this one and this one is the same as just now. These two are new, right? And then finally, there's one more case which is new as well, which is we pick some stuff from the top and we pick some stuff from the bottom, right? Because some stuff can be really near the bottom, right? It doesn't make sense to go all the way, like here, to get this one and then go back, right? So maybe you would do some from the bottom and do some from the top. That might be more shorter. Does that make sense? Okay, so again, let me try to ask a question now, just to see if folks are awake. I know this is a very heavy talk, but let me ask you a not so hard question. So, suppose we know all the positions along the aisle, where the objects are, right? So how do we decide, like, where is the point to split? Where is the point to split into the bottom and the top? Like how do we know? Or do we got to try every possibility, right? Can't be, that's very inefficient, many cases. Is there a way to decide which part should go top and which part should go bottom? What is the way, what is the thing you can check? Yes, that is correct. Exactly. So which one, how do you choose? So do you like bigger or smaller? Like how do you choose the distance?
Like the biggest distance you cut.
Yeah, exactly. That's a great solution. So we should look for the gap, right? I mentioned distance, but I mean I'll just say gap, right? So the gap between adjacent products, right? And we look for the biggest gap. Because how much does this save compared to this? E and F, right? It's missing this part, right? So the most savings you can get is when this distance is as big as possible. Does that make sense? Because that's where the savings come from. Here we go all the way up, all the way down. Here we kind of do this part and that part, right? So we're going to choose the biggest gap, or measure biggest distance. But we think of this as a gap. So we don't have to try every possibility, right? We just look at all the gaps. Which gap is the biggest, right? So a solution that does this, some up, some down, must break at the biggest gap. Okay. So almost done. And then this is the same thing, but now we have six arrows. It just looks a bit more complex, but it's kind of, in fact, it's the same code as just now, because if you look at my code, it just says generate cases. So it doesn't matter whether it's 6 cases or 3 cases. This same code still works, right? So that's kind of amazing. Okay, anyway, so let me finish up. So if you actually program this thing out, and we run it under some cases, under some situations, it turns out it will generate a solution to something like this. So here we are starting from this point, picking along all the axes, that's the products, and ending at the red dot. So this is a possible solution if you run through just now the algorithm. Okay, so let me end off. 5 minutes, good. What are some other things, right? Because this solves this pretty well, but it doesn't work when the number of cost hours is too many. So if you look at this thing, the problem is this term here. So there's still this exponential term. 7 to the power of h. H is the number of horizontal cross aisles. So when this h gets big, right, this will take a long, long time. So that's still obviously one big problem. So coming back to the video, which you didn't quite hear, but you saw, there was Amazon saying that, oh, we don't store all the one product in one place. We distribute it randomly all over the warehouse, right? If you didn't know, that was what Amazon does, but now you know, right? At least in this Singapore warehouse that they run a couple of years back, right? So you might think, that's not so obvious, because then for a given product, which of its many locations do I pick it from? Because the same product is in many places, right? So we don't just have the black dots. You might think we have dots of different colors, and you want to pick one dot of each color, where the color represents the product, and the location of the dots represent the location of that specific product in the warehouse, because there are many places where the product is stored. So that's actually not obvious how to do that. The other major problem, which I didn't quite talk about obviously, is this notion of batching. So again, you know, in the warehouse, you don't do one order at a time, right? Because you push a trolley, and then you try to fulfill multiple orders in one go, right? Because that's more efficient. So given a huge list of orders, like from yesterday night or whatever, how do you combine them, right? So that the picker can do like 5 different orders in one shot, right? Not one by one, right? So to efficiently make use of the picker's time. And this problem is called batching. It's also a very practical problem, but we don't have a good way to solve this. Okay, so in summary, I think we talked about many things. Hopefully, at least you remember a few key points. One is this notion of the traveling salesman and William Cook's fantastic talk in his book. And the second thing was this somewhat complex method, but which is fairly efficient for solving this warehouse problem, where the lines are only either vertical or horizontal, and there's a very fancy name for this called rectilinear. But in any case, the story was we only need to remember what happens on the boundary, right? It's either 0, odd, or even, and which component. Right? By doing this, we can solve all this in an effective way. That's the end of my talk. Thanks. Questions? Cool. Yes. Okay, cool. Let me run.
Just curious. There's so many branches. So actually, in the end, how do you choose which branch that will end up in the solution, or is there you choose which one ends in the end state, and then you just find all the branches that lead to the end state? So yeah.
That's an excellent question, because I totally never thought about that. Yeah. So what happens is for every one of this problem, right? So this is a problem ID in some ways, this thing, right? Because you can come to it from different ways, right? Because for the same kind of boundary, right? There are many ways you could reach this thing. Like some are the same, right? There's no example here, but there are many ways to get to here. So for all the different ways we come here, right? We just remember the smallest. So we have just a big dictionary of this problem ID and how many edges or how long were the edges used in total to get to this problem, right? And because we only want to keep the smallest, right? We don't have to care about all the rest, so we just throw away all the rest. We remember the smallest number that got to this position. Because we could have gone some other way and gotten here as well. Right? Yeah. Yes?
Yeah, thanks for your presentation. I think you... No, it's okay. Oh, okay. Thanks for the presentation. I visited some warehouse before, obviously. Like what you say, there's the X coordinate and the Y coordinate.
Yeah.
But likewise, there is also a vertical, like level 2, level 3, level 4. And to make things worse, sometimes they put fast-moving things outside and slow-moving things inside. I'm not sure if this OEE11 and this code takes care of this attribute. Thanks.
Yeah, thanks for the question. Actually, another thing to say is also people put things on the floor also in front of the shelf.
Yeah, sometimes they put things on the floor.
Yeah, so I know you've gone to the real warehouse, you're going to talk about all this, because I've also been there, and the story is actually not as simple as it looks like on the Amazon thing, right?
Yeah.
Where's the Amazon thing? Right, like this is, I think they were doing some filming, so it looks very clean. People put stuff on the floor, by the way, yeah? When they have no space, they put on the floor, they put in front of the shelf, they put in all kinds of random places. And as you say, warehouses have multiple floors, there's an elevator, right? You would take to go from one level to another level, yeah. So here, obviously, we've simplified the problem somewhat, right? Just like the physics thing, you know, every car is a sphere and so on. So, different levels, I would presume is easy, right? Because you would never do one level, go up, and then come back down again, right? That like makes no sense because taking the lift is a long time. So you would plan up one level with this method, right? And you can plan every level this way, and then you can join all the levels together afterwards. Yeah. But of course, if you say like, okay, there's stuff on the ground and all that, yeah, that unfortunately doesn't quite fit well into this formulation.
The stuff on the ground, but let's say if there's a particular location, outside they will put Campbell soup. Inside maybe they put medical equipment. Where the medical equipment maybe you only need it in half a year maybe once. But Campbell soup every day is stunning, you know.
So let me just end up because I'm out of time. So that's kind of a different problem, like where to allocate the position of an item, right? Like fast-moving goods versus like what you say.
Yes,
like, so in this problem, we kind of assume that we know where they are, that they've been decided. So we're just told to go here, this shelf, that shelf, and how to plan the walking path. Yeah, right. But that's an interesting problem as well. How to allocate shelves to goods. Okay, that's it. Thanks.